It's one of the things we need to know about because we do the whole idea of flame tests and try to understand why light from different colour comes when we heat or excite atoms. And so we need to think about the whole idea of the spectrum itself. You can see from here the spectrum is really a large range of different waves that travel at the same speed. We have a constant speed, and that's also in your constant section of your data booklet. But we only pick up the visible light, a very, very tiny part of this whole electromagnetic spectrum. Now, this becomes a little bit important when we're trying to explain how things happen, in other words, how the lines form and what they mean. All of the spectral lines are due to electrons, and this is the evidence we have for electrons and the fact they exist in these shells or orbitals, if you like. So what we know is that the electrons have a specific amount of energy, and that energy corresponds to the energy needed to be in one of these shells or subshells. The second thing we know is that the energy needed increases as you move further away from the nucleus. So in other words, the K shell requires less energy, the electrons in the K shell require less energy than the electrons in the L or M or N for that matter. All right, so as we go away, it's increasing the amount of energy needed. And this is important when we decide to move between these energy levels and create the spectra. Because there are so many of these possible energy levels, the electrons can move between them if they have the required amount of energy to exist in the next level. And this is one of the things that is key to the whole idea of spectral lines. Energy is really, really important in all chemistry and in spectra in particular. And the points I've made here are very important for us to realise that essentially everything in the universe is lazy as it will be allowed to be. In other words, it will have as least amount of energy it possibly can. All right, so if it's got too much energy, it will try to release the extra energy so it can go back to being lazy. And in normal times, this is released in some form of radiation. In class, I might have referred to something like me providing you more energy. If I hit you with a stun gun, cattle prod, whatever you want to call it, then you require, I could zap you with a bolt of electricity, so your energy, excess energy, comes out in movement and in sound. You yell. Electrons can't yell, that we know of anyway, so they remove it from themselves in the form of radiation. So it comes out in one of the electromagnetic waves that we've seen. So if we then transfer this whole idea through, we can see that because we've got fixed energy differences between the energy levels and the fact that electrons can move between these energy levels if we provide that energy into them, then what they actually do is they release a fixed amount of energy back out. And this corresponds to a particular wavelength or frequency of the radiation that we get. So the electromagnetic radiation from a particular jump will give a particular type of electromagnetic wave. Now, normally we'll talk about the amount of energy involved in this. Sometimes you might read in the textbook of a thing called a photon. Now, a photon essentially is a piece of radiation of a fixed amount of energy. So what does that mean in real terms? Well, if I have a large jump between what my excited energy level is and my normal or ground state is, then I am going to release a large packet of energy. Now, large packets of energy correspond to very short high-frequency electromagnetic waves. Things like X-rays and gamma rays and ultraviolet, high-energy ultraviolet. These tend to be a bit more dangerous to us, to humans and to life forms, than the lower forms. If I only have a small jump where the energy is relatively small, then it turns out that I will have a longer wavelength and lower frequency. Now, it's very, very important for us to think about this, because if the energy jump is too big, we produce radiation of very short wavelength and high frequency we cannot detect with our eyes or our senses. We have to use special machines to do it, like an X-ray machine or a scintillation counter or something to measure gamma rays. The same applies to if it's too small. Then we produce these long wavelength radiation that we also can't see, like microwaves. But occasionally, the jump is suitable and produces photons with enough energy to be seen, so we produce in the visible light spectrum. And each section of the visible light spectrum, each wavelength, corresponds to a particular colour, the 7 colours of the rainbow, and this is also found in your Chem data book, the IB Chem data book.